Today I will talk about how can we calculate the axial resolution of our spectral domain OCD setup. We need to calculate both the axial lateral resolution during the system characterization. So this is our OCD setup, and this is a laser. We are sending light in this path. This is the beam splitter. Light is splitting in this direction as well as in the sample arm path. The reflecting back for both from the sample arm as well as from the reference arm, and they are making interference here, and we are getting the interference signal from the line scan camera. So we will see like this kind of image. Now one thing that's very important is that what is the axial resolution or the lateral resolution. What does resolution means actually? It means that like how small objects you can see. If resolution is pretty good, that means if resolution is small, that is you will be able to see the small things like sail or other stuff which are very important. So now first I will talk about the axial resolution. So for the axial resolution, it tells you that how far, like how small things you can see in z direction. In z direction, how small things you can see. So the equation of the axial resolution is this, where del z is the axial resolution. These are constant parameter. If you notice that the axial resolution only depends on lambda. Lambda is the central wavelength of your laser source, and del lambda is the bandwidth. So it doesn't depend on the beam focusing or the spot size. So it doesn't depend on the how much objective or what is the numerical aperture or objective. It doesn't depend on that. So if the bandwidth is fixed, if this is fixed, then we can see that axial resolution only depends on the wavelength. Or either way, if the wavelength is fixed, it will inversely proportional to bandwidth. Say, let's see the graph here. One of the graphs say, let's first focus on that. Our bandwidth is, say, for example, 150 or 100, say 100. So we can notice that for 1300 nanometer, the resolution is bad because wavelength is higher. As it goes downward, resolution becomes good. That means the 800 nanometer setup has better resolution than the 1300 nanometer wavelength data. So we want a small wavelength data. So that axial resolution will be, we want a small wavelength laser source, so that we can have good axial resolution. Also, if you look at, if we increase say from 100 bandwidth to 200 bandwidth here, we can see that the resolution also improves. So we also need to have a good bandwidth laser source. So to have a good axial resolution, either we have to increase the bandwidth or we have to increase we have to decrease the wavelength, central wavelength. Say, for example, say in our case, in our setup, the setup that we have in our lab, one is 800 nanometer setup. So lambda is 800 nanometer and del lambda is say 170 nanometer. So if we calculate the del z, what is the del z we find? Say here in MATLAB, so lambda is 800, bandwidth is 170, and axial resolution, if you use this formula, then if we run this one, and we'll find that axial resolution in nanometer is 1.66. So axial resolution is 1.66. 1.66 microns. So this is a theoretical calculation, but in practically you will find that the resolution will be a little bit higher because of the noise or the which position we are taking the image. So one thing that we need to know before going for the actual calculation of the axial resolution is that how can we convert the pixel value into the physical distance. Say for example we are taking image of the sample whose thickness is 90 microns. Say for example this thickness is 90 micron. If we look at the image, say this is our image, actual image, this is the one cross-sectional image, and if this 90 microns, this image in cross-sectional is in between, say for example 42 pixel to say 112 pixel, that means here the pixel distance is 70 microns and our actual physical objects is 90 microns. That means 1 pixel equal to 1.3 microns, that is 90 divided by 70 equal to 1.3 microns. So if we have a depth profile, say for this image, say if we have a depth profile something like this, if initially the depth profile is in pixel, so pixel, this is height, and we can convert this pixel value into micron value just by multiplying the pixel, the x-axis into 1.3. That means after new pixel will be a new x-axis will be in microns. Say okay, so these are the basic things we need to know to convert the pixel into physical distance. Now to calculate the axial resolution of a particular system, what you need to do is in the setup we have to put the mirror here instead of this MEA. We will put one mirror because mirror is highly reflective and the reflection will come from the top of the surface. So we will only see in the depth profile, we will only see like this kind of peak from the mirror. So we have to take the data from the mirror, and this is the depth profile we got from the mirror. Here in y-axis is the intensity in dB and x-axis is the depth in micron. And so what we need to do is we have to figure out what is the full white half max. If it is in dB, so what we need to do basically is we have to see here what is the maximum value here. Say here maximum value is 90 dB, so the half power value will be at minus 3 dB point. Say like here minus 3 dB point will be whatever the value here. So we have to check actually minus, as it is in dB, that means minus 3 dB. So 90 minus 3 equal to 87. So we have to look at what is the width of the beam at the 87 pixel. So if this is peak is 90, so whatever here is minus 3 dB point. So we have to check here what is the distance between these 2 points, this point and this point. So for our case we have find that this around like 2.7 microns. So 2.7 microns. So in this way we will be able to detect what is the axial resolution. So it means that, so this 2.7 microns means that we will not be able to see anything smaller than 2.3 microns in axial direction. So anything we have to see clearly, if you want to see clearly, that should be greater than 2.7 microns. So in this way we will be able to detect the axial resolution of our OCT setup. In next video I will talk about how to calculate the lateral resolution of our OCT system. Thank you very much.